Hi everybody, today we're going to learn how to use orbital diagrams or orbital charts to help us write an electron configuration. What the orbital diagram is going to do is it's going to tell us what order the electrons go into the orbitals. So your orbital diagram can look lots of different ways. This is the one that I like. I like that it uses the gray bars to help you see where the energy levels are. I like that the boxes are labeled. You can find all sorts of versions of this online. But the orbitals will always go in the same order regardless of what the formatting looks like on the chart. So just a reminder of our electron configuration rules. We have the Aufbau principle, which says we're going to fill from the lowest possible energy level first. The silly way to remember this is that they are lazy. So if this is our orbital diagram, you can see here energy is increasing going up. So this is the lowest orbital. I'm going to start by putting electrons into the 1s orbital. When it's full, the next highest is 2s. When that's full, 2p. When that's full, 3s. When that's full, 3p, and so on. So we will be going from the bottom to the top. Our next configuration rule is Pauli exclusion principle. This is the one that says that no two electrons can have the same set of 4 quantum numbers. Basically, they need to have a unique address, otherwise they would not be different electrons. If they had the same quantum numbers, they would be the same electron, so they must be unique. What that means for us in a practical sense, trying to use this chart, is that inside an orbital, you can only have 2 electrons. One of them needs to be spin up, and one will need to be spin down. So if we're looking at our orbital chart, orbital diagram, inside one of these boxes we're going to draw an arrow up and an arrow down. That would represent 2 electrons. We always do spin up first and then we do spin down. It's kind of classic to use these half arrows because the boxes are so small. It's very helpful to use half arrows. Do not try to squeeze in a full arrow. You can use these little half ones. The last is the one that I think is a little bit hardest for people until they do some practice, and that's Hunds Rule. So Hunds Rule says electrons will fill each equal energy orbital before they pair up. So what we're going to do is we're going to spread the electrons out, and then we will go back and double them up. The analogy I like is that you don't want to have to share a bedroom with your sibling unless you really, really have to. Right? Electrons are negatively charged objects, and you don't want to squish 2 negatively charged objects close to each other unless you really, really have to. And so because of that, they're going to want to spread across all the orbitals possible before they have no other choice. So if we were to look at, let's say, the 2p set of orbitals, the 2p set has px, py, and pz. I'm going to put 1 in px. I'm going to put 1 in py. I'm going to put 1 in pz. Now they each have their own bedroom. Now they're all full. We don't want to go up to a higher energy level yet because there's still room here. So now we're going to double up. Now we do spin down px. Right? And we would keep going. We would put 1 here and 1 here if we needed to. Okay? So a reminder of the steps from our last lesson. Once you know which atom you have, you're going to find out how many electrons it has using the periodic table. Then we're going to start using our orbital diagram and chart. We're going to make sure we follow our 3 rules. And then we will list which orbitals we used and how many electrons were in each one. When we do that, we have the final configuration. So let's do some practice together. I'm going to do this part under the document camera. So give me a moment. Let me drag this over to the screen. All right. So I have my little printed chart. We're going to use this like a set of notes. So you will be taking little notes on the diagram and off to the side. In order to kind of practice our rules, we're going to pick an atom. We're going to do a giant one with 84 electrons in it. Big atom. That'll give us a lot of electrons to practice with. Remember, I'm trying to get my periodic table out here. Remember on your periodic table, to find the number of electrons, you look at the atomic number unless it's an ion, and then you adjust. This is neutral, so if I have 84, right, protons, that's telling me I also have 84 electrons. So we're going to have to follow our 3 rules. We have Aufbau. We have the Pauli exclusion principle. And we have Hunds Rule. So those are the 3 that we're going to need to follow. So let's start with rule number 1. Start at the bottom. I'm going to put my first electron here, spin up. Now I need rule number 2. Rule number 2 is that 1 electron goes spin up and 1 goes spin down. So they have unique quantum numbers. So my second electron will be here, spin down. Now I need number 3 and number 4. Here's number 5, and now at this point I need to use Hunds Rule, which says that I need to spread them out then pair them up. So 1, 2, 3, 4, 5. Here's number 6, number 7. Now number 8 is spin down, 9 is spin down, 10 is spin down. Now this is full, so I go to the next one. Spin up and spin down. Now right here, this is Hunds Rule again, right? One, 2, 3, 4, 5, 6. Spin up, spin down. And now you need to be a little bit careful. We still have to follow Aufbau, right? But look, these d orbitals are the lowest as of right now, not the 4p. I'm going to go from 4s to 3d. Then once those are full, then I can go to 4p. Then the next lowest would be 5s, and so on. So you have to be really careful because they're not going to come in numerical order every time. It takes less energy to put electrons in the 4s orbital than it does the 3d orbital. Even though they are physically in the third energy level in terms of distance from the nucleus, that doesn't mean it takes the same amount of energy as the rest of the 3p and 3s orbitals. Because these are very complex shapes, because of their size and everything, it actually is a little easier to do the 4s. So it kind of cheats. It goes from 3p to 4s, and then it doesn't really have any choice. It has to go to the next lowest, which would be the 3d. So off to the side, I'm going to put a little note that says, careful to, quote, zigzag up the chart. We need to always go lowest to highest energy. Even if that means we're going in a funky order. So I'm going to go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. Now is the first time I ever finally get to fill out a 4f. Then 5d, then 6p, then 7s. Then we get to do 5f, 6d, and at the very end, 7p. So this giant pink mess is basically showing you that you have to kind of zigzag your way up, making sure that you are always following Hunds Rule, right? Hunds Rule is telling us that we got to zigzag up and down that chart, right? So let's fill out all of our electrons, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, all the way over here, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84. Oh, that was a lot, okay? Let's list this out as a configuration. So I started with the 1s orbital, and there were 2 electrons in that box, so my superscript is 2. Then 2s, 2, 2p, 6, 3s, 2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, so at this point I've really run out of space, right? So I'm just gonna continue down here. So 5p6, 6s2, 4f, and if you count, there's 14. 5d10, 6p, it's not 6. How many are here? 1, 2, 3, 4. So one of the things you got to be careful of is that you're not on autopilot and you don't just keep going and go all the way to 6. If you stopped early, we didn't have 6 up here. We only had 4. So all together, say it out loud with me. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p4. And that, all 84 electrons, is what polonium's electron organization is, right? This is its electron configuration. Okay, so let's do a couple more practices. Now, one thing you might see are what I like to call a space-filling orbital diagram. Instead of going vertical, which takes up a lot of space, you can draw them horizontal. This is really helpful on homework in your binder paper when you're doing a warm-up or something too, where you want to not use quite so much space. You don't want to have to print these little charts out every time. You can just draw a line for each orbital and go across, and it'll really save some space. So let's do chlorine. Chlorine has 17 electrons. The 1s orbital is the lowest energy. 1, 2, 3, 4. Here's p orbitals, be careful. 5, 6, 7, 8, 9, 10, 11, 12. Back to some p orbitals. Do Hunds Rule. 13, 14, 15, 16, 17. So if I want to write my configuration, I'm going to say 1, S2, 2, S2, 2p6, 3s2, 3p5. One thing to notice, poor little chlorine over here has an electron that's all by itself. This is an unpaired electron. That is a sad thing. Okay? Chlorine desperately wants to steal an electron from another atom to fill this missing spot. Chlorine is very reactive. It likes to make a -1 ion because it's trying to steal from something else to fill this gap. So looking for these unpaired electrons can tell you how things behave. Okay? All right, I'd like you to try iron, which has 26 electrons. All right, 26, here we go, ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. D orbitals, 21, 22, 23, 24, 25, 26. So this is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6, 3d6. Okay, let's try another one. "37 electrons this time. Remember, you got to do all 3 of your rules. You need Aufbau starting at the beginning. You need Pauli exclusion principle, putting 2 electrons in each orbital, 1 spin up, 1 spin down. And you need Hunds Rule anytime you have multiple orbitals at the same energy, that you spread them out before you double them up. So try 37 electrons. All right, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Careful, d orbitals. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. P orbitals. 31, 32, 33, 34, 35, 36. And last one, 37. So you can see here, we have an unpaired electron. One thing that's interesting is sometimes it's easier for an atom to lose an electron. Rubidium likes to get rid of this one. That means that its 4s and 4p orbital would be nice and full, which it would prefer. We'll learn a little bit more about that later. But sometimes they may lose an electron, like rubidium. Sometimes maybe they gained an electron, like chlorine. Sometimes things get even more complicated, like iron. We'll learn about how some metals, like iron, can do lots of crazy things. But we'll learn a little bit more about that later. All right, let's do a big one. Last one. Let's do tin. 50 electrons. Oops, we should probably write out our configuration here, huh? Okay, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1. You do need to put the 1, by the way. You can't just leave it off. It's not like math class where you don't have to say 1x. You do have to put the 1 there. All right, now try doing tin. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50. So tin has 2 unpaired electrons. One of the reasons I'll ask you to practice counting your unpaired electrons is that's a way I can turn an electron configuration or an orbital diagram into a multiple choice question. I may just ask you, how many unpaired electrons does tin have? And if you don't understand how to spread your electrons out correctly with Hunds Rule, you're not going to be able to figure out that there were 2 unpaired. So that's a way I can ask you a question in a multiple choice format and double check that you understand what Hunds Rule is trying to tell you. All right, let's write our configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p2. All right, everybody, that was it. We learned about it. We learned how to use our diagrams. We did a couple practices. It does take time to get good at this. It takes lots of practice to get good at this. I think doing them out loud will really help. We're going to practice this on some worksheets, and then the next lesson will be me teaching you the periodic table trick so that you can do this with nothing but a periodic table in front of you. I don't need an orbital diagram. I don't need an orbital chart. I can just look at my periodic table and I can see all sorts of patterns in here that we'll be able to see from the periodic table alone. All right, everybody. Hope that was helpful. Bye.